Let us now focus on the electrons in an atom. Let us begin by remembering Ernest Rutherford's model of an atom, which is also called the nuclear model of an atom. According to Rutherford, the electrons in an atom are located outside the nucleus of an atom. This is the question we want to answer. How are the electrons distributed in an atom? How are the electrons distributed in an atom? That is the question. And to answer this question, let us first remind ourselves that J.J. Thomson discovered electrons. And when J.J. Thomson discovered the electrons, one of the things he found is that electrons are particles, which means that each electron has a certain mass, which is another way of saying that each electron in an atom is a piece of matter. But later researches found out that electrons also have wave properties. Also behave like waves. And this is the question: what is a wave? Let us try to answer that question. A wave is a disturbance that travels by transfer of energy. A very simple demonstration of a wave is to drop a piece of stone in water. The disturbance generated will be transferred away from the point of disturbance, and this will lead to a wiggly wave, which is also known as transverse wave. Let us now understand what is a transverse wave. If you tie a piece of rope to a tree, a transverse wave will be generated. Now, the highest point of the transverse wave is known as the crest of the wave. The lowest point of the wave is known as the trough of the wave. The distance between any two adjacent points on the wave, for example, the distance between two crests or two troughs, is known as the length of the wave, also known as wavelength. Wavelength has a Greek symbol. The Greek symbol looks like this. It is called lambda. So, to determine the wavelength of a transverse wave, all you need to do is measure the distance between two crests or two troughs. Since wavelength is a measure of distance, The SI unit of wavelength is meters. Another important property of a wave is its frequency. So what is the frequency of a wave? The frequency of a wave is the number of wave crests to pass through a fixed point in a second. The unit of frequency is per second, which is also known as hertz. The Greek symbol for frequency is nu. The question then is this: is the wavelength of a wave related to its frequency? Yes. The relationship between the wavelength of a wave and frequency can be written as an equation. The wavelength, which is denoted as lambda, multiplied by the frequency, which is written as nu, will be equal to the speed of the wave. Remember this relationship. Now, to properly understand electrons, it is extremely essential to understand light. Why is light important in this discussion? The reason is because light also behaves like electrons. Light is both a particle and a wave. So let us learn about light. Light is an electromagnetic radiation. What does that mean? It means that when the electric field interacts with magnetic field, the result of the interaction is what is known as light. And since light is also a wave, the product of its wavelength and its frequency is equal to the speed of light, which has an approximate value of 3.0 times 10 to the power 8 meter per second. Let us now dig a little deeper into the relationship between the wavelength and frequency of light. This relationship is captured properly by the electromagnetic spectrum. What does that mean? If you have the interaction between the electric field and the magnetic field in such a way that the wave generated is well spaced out, the distance between the crests or the troughs are very far apart. This is said to have long wavelength. That is, the wave can travel a long distance, or low frequency, which means that the wave is not coming very fast. That is another way of saying that the wave has low energy. An example of such a wave is the radio wave. On the other extreme end of the electromagnetic spectrum, If you have a wave in such a way that the wave crests are very close, which is another way of saying short wavelength or high frequency, which means the wave is coming very fast at you. And if the wave is coming very fast at you, it will hit you with a very high energy. An example of such a wave is the gamma ray. In between these two extremes are other electromagnetic radiations. For instance, the next low energy electromagnetic radiation is the microwave. We all know what a microwave is. We use it in our houses. The next low energy electromagnetic radiation after the microwave is the infrared. Now, what is the infrared radiation? It is another way of saying heat, whether it is the heat generated by a stove or by the body of a living thing. The next radiation after infrared based on energy is the visible radiation, which we generally call light. This simply means the light that is visible to we human beings. And the longest wavelength visible light is red, followed by orange, then yellow, then green, then blue, then indigo, and lastly violet. Violet light is the shortest wavelength visible light. The next electromagnetic radiation based on energy is the ultraviolet radiation. That is the radiation you get from the sunlight. And the last of the lot is X-ray. It is the next higher energy electromagnetic radiation. Let us now take a look at a calculation on the relationship between the frequency and the wavelength of light. A light has a frequency of 7.50 times 10 to the power 14 Hertz. Nu, which represents the frequency, is given as 7.50 times 10 to the power 14 Hertz. What is the wavelength of this light? We are being required to find lambda, which represents wavelength. Given that the speed of light, which is usually represented as the symbol c, is given as 3.00 times 10 to the power 8 meters per second. We know the relationship between frequency and wavelength. The wavelength multiplied by the frequency will be equal to the speed of light. If we rearrange this equation such that we isolate the wavelength, then the wavelength will be equal to c divided by nu. If we plug in the values, the speed of light is given as 3.00 times 10 to the power 8 meters per second, while the frequency is given as 7.50 times 10 to the power 14 Hertz. If we divide, we should get 4.00 times 10 to the power -7 meters. And if we convert this to nanometers, we should get 400 nanometers, which is usually the unit that is used to represent wavelength.